Okay, today we'll see about the program flow mechanism. Here you can observe there are two diagrams. Diagram A shows the global architecture in which we have different processing elements. There are n number of processing elements which are connected to n by n routing network. So the data from one processing element can go to any other processing element with the help of this routing network. So there is a global path for each and every processing element. So this diagram shows the global architecture, how exactly the data flow is happening. In diagram B you can see the interior design of a processing element, how exactly the processing element look like. So here we have the ALU to which the token match is generated and it is sent to the ALU, and from the ALU after processing the data it is given to the from token. From there it is going to the routing network. So as you can see in diagram A, the data can flow from the routing network outwards, and also data is coming inwards the routing network. So here from token it is going to routing network, and at the top you can see the data is coming from the routing network. So there is a local path for each and every instruction. So this is the structure wherein we have the data flow that is coming from routing network, and also it is given to token match. So this is how it is going to look like processing element. Here we have compute tag. So for each and every processing element they should be given some tag that is taken care by this compute tag. Then we have program memory. Memory in the sense whatever data is required that is stored in the program memory. It is in either direction, that is from the token match it is sent to the program memory, and from program memory we can send back the data to the token match. So this is how program flow mechanism look like. Now these are the some of the examples given, a sample program and its data flow graph. That is diagram A. Diagram B has sequential execution on a uniprocessor in 48 cycles and data driven execution on a 4 processor data flow computer in 14 cycles, that is diagram C. So if you observe in diagram 4, it is parallel execution on a shared memory 4 processor system in 14 cycles. Now coming to the next slide, system interconnect architectures. So how exactly it is interconnected with the different parts of the architecture. So there is direct network for static connections, also indirect networks for dynamic connections. Then network properties and routing has got these attributes which are static networks and dynamic networks. The network size, what is the size of the network, then node degree, that is how many nodes are present in our system, in degree and out degree, both are considered here. The network diameter, what is the diameter of the network, then bisection width, if you take the bisection, what is the width, that is also given here, which has got the sub properties like this: channel width given by W, channel bisection width given by B, wire bisection width B is equal to B dot W. Then we have wire length, then symmetric networks. So these are with respect to system interconnect architectures. Then we have one more, that is network properties and routing. So data routing functions are there. So what are those functions? shifting, rotation, permutation, broadcast, multicast, shuffle and exchange. And one more attribute is hypercube routing functions. So this shows the perfect shuffle and its inverse mapping over 8 objects. So here we have 8 different objects. This is perfect shuffle and inverse perfect shuffle. So how exactly shuffling is happening, that is shown in these two diagrams. So these diagrams are related to that only. A 3 cube with nodes denoted as C2, C1, C0 in binary. Then routing by least significant bit, that is C0, that is shown by this. Then we have routing by middle bit, that is C1. So C1 is here. Then finally we have routing by most significant bit C2. So these are with the different significant bits, how exactly it is going to look like. Then system interconnect architecture has also got network performance. We have to find out the network performance by functionality, network latency, bandwidth, hardware complexity, scalability and network throughput. Network throughput has got 2 attributes: total number of messages the network can handle per unit time and hotspot throughput. So these things have to be calculated whenever we come across any problem. And next we have static connection networks. So here we have linear array, ring and chordal ring, barrel shifter, tree and star, fat tree, mesh and torus, systolic arrays, hypercubes, cube connected cycles, K-array n cube networks. Then summary of static network characteristics. So there is a table by the number table 2.2 that should be referred for this particular summary of static network characteristics. So this shows the different networks. This is ring network and these are all the different types of networks that are available. Then we have binary tree. As you all know how binary tree is present. So this shows the binary tree network. This is star network and binary fat tree. This is binary fat tree. Then we have mesh, iliac mesh, torus and systolic array are given by these diagrams. So these are all the different types of interconnect architectures. These are some more sets similar to that. And one more we have, this is quite complex, that is the K-array n cube network shown with K is equal to 4 and n equal to 3. Then we have dynamic connection networks, wherein we have bus system, digital or contention or time shared bus, then switch modules, binary switch, straight or crossover connections, multi-stage interconnection network, then interstage connection, omega network, baseline network, crossbar network, summary of dynamic network characteristics. So these are all the different types of network architectures that are available and also the parameters for them. Then so there are so many different types of performance evaluation of parallel computers. So CSE 539 is the model given basics of performance, performance metrics, parallel runtime, speed up, efficiency have to be calculated. Standard performance measures are given by peak performance, sustained performance, then instruction execution rate and floating point capacity. Then we have parallel runtime. The parallel runtime given by T of n of a program or application is the time required to calculate the program on a n processor parallel computer. When n equal to 1, T of 1 denotes sequential runtime of the program on a single processor. And speed up is given by S of n is equal to T of 1 divided by T of n. Then efficiency is given by E of n is equal to S of n divided by n, and that is equal to T of 1 divided by n into T of n. So this shows the graph with the relationship between T of n and the number of processors. So number of processors are given on x-axis, execution time is given on y-axis. So execution time versus number of processors employed is the graph that is shown. You can observe the curve here, graph written like this. So this shows the relationship. And we have speed up versus number of processors employed. So speed up and linear, sublinear lines are there. Similarly, we have one more graph showing the relationship between E of n and number of processors. Then we have to find the standard performance measures, which is peak performance, sustained performance. Then benchmarks are set of programs of program fragment used to compare the performance of various machines. So some examples are given for this. Then inter-processor communication has got load imbalance, inter-task dependency, extra computation, parallel balance point. Speed up performance loss is given by Amdahl's law and Gustafson's law, Sun and Nee's law. Amdahl's law is given by, for a given problem size, the speed up does not increase linearly as the number of processors increase. In fact, the speed up tends to become saturated. So this is Amdahl's law. This is a consequence of Amdahl's law. According to Amdahl's law, a program contains two types of operations, completely sequential and completely parallel. So Amdahl's law is given by Ts is equal to alpha into T of 1 and Tp is equal to 1 minus alpha into T of 1. So here we are assuming that the parallel operations achieve linear speed up. So T of n is equal to Ts plus Tp divided by n, that is equal to alpha into T of 1 plus 1 minus alpha into T of 1 divided by n. Thus the speed up with n processors will be given by this particular equation.